All right, so in this video, we're going to talk about power series. And you can see a power series is a form of an infinite series, but what's different is that we're not just dealing with the index in the actual formula here. We have an additional x variable. And so as you can see, if I expand this out, this is what I'll come up with. And you can again see the x's as part of the sum. Similar down here, we've got a more general form where instead of just the x, we have an x minus c. And once again, there's its expanded form. So for that first one, many times we will say that this is centered at x equals 0. And this guy we'll say is centered at x equals c. And so the question that we're going to ask when it comes to these power series is what values of x will make them converge or diverge. And so that's where this theorem comes into play. The theorem says consider the power series, then exactly one of the following is true. So we know we can always push a power series into convergence because in this case here, if we let x equal c, then all of a sudden we have a sub n times 0, and the sum of a bunch of zeros would converge to 0. So we can always push a power series into convergence. And that's what this first part says. It says it will converge at C, or can converge at C, and diverge for everything else. The second part says that it converges for everything. So no matter the value you plug in for x, this thing will converge no matter what. And the third case says that it'll actually converge on an interval, so within a radius of C. So C plus R and C minus R, convergent, and then divergent outside of that interval. Now, we will also talk about things, interval of convergence and radius of convergence, and you'll see that come into play in the next few examples. But just to kind of summarize a little bit, this guy right here denotes that radius of convergence that you'll hear me talk about, ROC. And on 1 and 2, we still technically have a radius of convergence to talk about. We just say that R in this case is going to be equal to 0, and then R is equal to infinity in this particular case. So once we take a look at a couple examples, hopefully that'll start to make a little more sense. But remember, we're taking a power series, we're trying to figure out what it's going to take to plug in for x to make it converge. We automatically know that if we plug c in, it can converge to 0. It could also possibly be any x value, or it could possibly be any x value on an interval for a particular power series. All right, so we'll take a look at this first example here. You can see we have a power series now, in this case centered at 3. And so we're going to try to determine what values of x would make this thing converge. And so generally speaking on these types of problems, moving forward with the ratio test is the easiest way to get an immediate result. So by the ratio test, I'll go ahead now and set up my limit as n goes to positive infinity. And if you'll remember, the ratio test will have the absolute value bars on it. So in this case, when I put the absolute value bars on it, this guy becomes negligible, so I'm not going to worry about it. But I am going to go ahead and put the absolute value bars there still. I have an x minus 3 raised to the n plus 1 over 2n plus 3. That comes from me putting an n plus 1 right here, distributing and combining. And then divided by the original function. So as you've seen in the past, that's going to be us multiplying by the reciprocal. So we'll have this 2n plus 1 over here over x minus 3 raised to the n. And so again, I mentioned the absolute value bars would do away with this, but I still have them here. That's because of the x minus 3's. We don't really know what's happening there yet, so we still need to consider the absolute value bars to make sure we don't take any negative values. So when I go ahead and I simplify this now, I'm going to have the limit as n goes to positive infinity. And as you've seen in the past as well, this guy right here can divide off with this guy right here, leaving us with this x minus 3 now to the first. So I'll have my x minus 3 to the first, and then I'll have the 2n plus 1 over 2n plus 3. So I'll go ahead now. Remember, the limit is with respect to the n. All they care about is n. So this guy not having an n, I can technically pull outside. And that's one of the reasons, again, I think it's important to keep those absolute value bars at the top of your mind, because when you pull that out, that's going to be an absolute x minus 3. Then we have the limit, as n goes to positive infinity, of 2n plus 1 over 2n plus 3. At that point, when you're talking about n's, you don't need the absolute value bars anymore because n goes from 0 to infinity. And so this limit's just a very straightforward limit. So this guy here goes off to 1. And so really what I have left is this absolute x minus 3. Now remember, we're trying to push this into convergence. Having used the ratio test, I want to make sure that that output is less than 1. Right, that's going to be the condition of the ratio test for something to be convergent. And so now I have the inequality, the absolute x minus 3 less than 1. We can solve this using a little bit of algebra. -1 less than x minus 3 less than 1. And so then I would have a 2 less than x less than 4. So this is a good starting point figuring out now the interval of convergence. The problem is, though, we have to test the endpoints. We always have to test the 2 and the 4. That's also because of the condition from the ratio test. Remember, if the output is 1, the result is inconclusive. And so notice, if I put a 4 in, I get a 1. When I put a 2 in, I get a 1. And so because of the 1 being inconclusive, I always need to test the endpoints. Okay? So what I'll go ahead and do here is I'll just put a little line down here. I'm going to start by testing x equals 2. So if I test x equals 2, I'm going to come back in here to the original. I'm going to put a 2 in right there, x equals 2. That's going to give me now the infinite series of a -1 to the n times a -1 to the n over the 2n plus 1. Now, we know the -1 to the n, these are alternators. If they're both positive, they're both positive. If they're both negative, then we multiply and we get a positive. So in reality, what just happened is we're able to simplify now and be left with 1 over 2n plus 1. So now I need to determine if that is convergent or divergent. So what I'll do here is I'll go ahead, I'll consider the series 1 over n, which diverges by harmonic, and I'm going to use the limit comparison test. Now you can use whatever test you want to in determining whether or not this converges or diverges. The limit comparison is a very direct, very quick one, comparing it with the harmonic. So as I run the limit comparison on this, I'm going to have the original, which is 1 over 2n plus 1, divided by the one I'm comparing it to. So I'm going to flip that in back around. And you can see that ends up being a quick 1/2, which is bigger than 0. Therefore, diverges by the leading coefficient, or not the leading coefficient, that's the limit comparison test. So what we know so far is that if you plug a 2 in up here, this thing diverges. Okay? So now we still have to test the 4. So maybe I'll separate right here. I'll say let x equal 4. If we let x equal 4, once again going into the original, that's going to be a +1 to the n, and that +1 to the n is just going to be a 1 no matter what. So we're going to just now have the -1 to the n over 2n plus 1. Well, now that's an alternating series. So when I take the limit as n goes to positive infinity of just the 1 over 2n plus 1, the fact that that equals 0 implies that it's absolutely convergent by the alternating series test. So again, we've determined from this part right here that the 2 causes the series to diverge, But from this stuff right here, that the 4, if you plug it in, still gives you a convergent series. So, as a conclusion, kind of in summary, the interval of convergence, IOC, interval of convergence, starts with this guy, 2 to 4, but we found that we need to include 4. So we're going to have 2 to 4 inclusive on the 4. And then the radius of convergence, that's going to be an r equals 1. If you remember, we were centered at 3. So 3 is the center. If 3 is the center, we go 1 unit to get 4. We go 1 unit back to get 2. So our radius of convergence would be 1 in this particular case. So in summary, when you're given a power series like this, many times I'll start with a ratio test. It's very mechanical. We set the absolute value. Remember, the absolute value is important. Less than 1, because that's the condition in which the series would converge under the ratio test. Solve the inequality. However, you always have to check the bounds, because the bounds are what would make this equal to 1, which would be inconclusive. So by testing the bounds and plugging the value in, we plugged a 2 in, we plugged a 4 in, then it's a separate problem to determine convergence or divergence for the series, having plugged in the respective numbers. Once you have that, then from there you can establish the interval of convergence and the radius of convergence.